Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to discuss recursion with fractals. In a previous lecture, we started discussing recursion, which is a way we can start solving problems by solving smaller versions of the exact same problem. Now, recursive methods are loop-like. However, they do utilize the call stack in order to afford us elements like backtracking. Now, as a reminder, recursive methods require some kind of halting condition in order to stop recursion, and also a recursive call. As an example over here, this recursive method called countdown simply stops whenever this I is less than 0, but if it's not less than 0, then we keep subtracting 1 from I and recursively calling that 1 at a time. In order to further explore how this is going to work, let's take a look at this problem called Sierpinski's carpet. The main idea is given some sort of region. So we're given some sort of x and y coordinate and also some sort of length. So given a region, what we do is we cut that region into 3 horizontal and vertical slices. We then fill the center square, and then we repeat this process for the surrounding 8 areas, until we've reached either a recursive depth or some sort of pixel limit. So what you see over here is an example of a Sierpinski carpet, where, as you could see, this is the center square if we divide this up into 1, 2, 3, 1, 2, 3 elements here. And then this is the exact same problem, but a little smaller, where we've divided it into 1, 2, 3, 1, 2, 3, filled the center square, and then in a smaller version here and a smaller version here. In regards to how we can solve this using recursion, we have to figure out how we can solve a smaller version of the exact same problem. So let's look at it like this. If we are given this region, and assume right here, we have the starting coordinates x and y, which are always going to correspond to the top left coordinate. This is very important because our origin, the x and y, is always going to be assumed to be our top left. Now, given that x and y coordinate and also the length of one of these sides, which we'll just call s, the first thing that we have to do is divide this into 9 regions by simply dividing s by 3. So this gives us 1, 2, 3 vertical, 1, 2, 3 horizontal, 9 different squares. Now what we have to do is just fill in this center square. In order to do that, we also recognize that we're always going to be drawing starting from this top left coordinate, and then we can fill in this square by simply giving the size, the length, and the width of this square. Now, before we can start doing that, we still need to calculate what is the position of this coordinate given what we have so far. We only have the xy, this top coordinate, and the length of this side. In order to get this coordinate right here, all we do is take the starting coordinate x and then add a third of the width. So x plus this side divided by 3 gives us this position here. Now similarly, what we do with the y-coordinate is the exact same thing. If we assume that this y-coordinate starts here and y increases downwards, if we assume that, then in order to get this position right here, we take this starting y-coordinate, here is our origin, and add 1/3 of that side, getting this position. And this is how we can calculate this coordinate right here. Now, given that we have this x and y coordinate, which is assumed to be right here, and this width and this height, which is assumed to be 1/3 of this, we can then feel safe and filling in this square. Starting from this coordinate, then starting from here, plus 1/3, and plus 1/3, we can simply draw this square. The smaller problem that we are solving is we are dividing the region into 9 squares and filling in the center square. Now we can use this solution in order to solve a much larger version of the exact same problem. We start recognizing that basically this solution of drawing this center square is the exact same solution we need to apply to this region, this one, this one, this one, this one, this one, and this one. The only thing that we need to change is where this x and y starts and the length of the side. Let's say that we were now going to draw the center square in this region right here. The first thing that we recognize is this region is basically starting from the exact same x and y coordinate, in other words, the same top left coordinate, but this region is 1/3 of the size of this entire region. So basically now, if we subdivide only this region into 9 parts, it would look like this. We're still starting from the same x and y, but now our region is smaller because one of these squares is 1/3 of 1/3. So in other words, it is 1/9 of the originally given side. And so starting from this top left position, we just need to calculate this coordinate right here. And now this is x plus 1/9 and y plus 1/9. That gives this coordinate right here. Now filling in, understanding that we're drawing this as a 1/9 by 1/9 square, it'll simply look like this. Now remember, this only took care of top left, but remember, including this one, we have 8 recursive calls that we have to worry about. Let's see what top middle looks like. So now, looking at our top middle right here, the thing is, when we were starting here, we were given this x and y, and we had to first initially draw this center square given this length of this side. When we did this again for this top left region, the x and y didn't change. The only thing that did change was the length of the region. But now, we have to once again assume that the x and y is the starting coordinate given this region. In order to calculate where this region starts, what we do is given this x coordinate here, we basically move it over. We translate this over by 1/3 of the side. This indicates that this region starts at the x position plus 1/3 of this side. The y doesn't change. This y is the same coordinate as this y right here. Now given that, we once again take 1/3 of this side, which is now 1/9, but now we take 1/9 starting from this x position, move it over, and given the same y position, we move it down, and then giving 1/9 by 1/9, we could draw the center square. Now applying this all the way down here, it basically looks like the same thing. Now we have to figure out where this starting coordinate is, which in this case is given this x. This is x plus 2/3 of this, and y plus 2/3 of this side. So this is where this x and y starts right here. Now given this 2/3 plus 2/3, we can now add 1/9 and 1/9 in order to draw that center square. And so we do this until we reach that halting condition, which either could be a pixel limit or some sort of recursive depth. Now, applying all of this together, we're going to see how to do this in code, and we're also going to introduce creating a graphical user interface in order to do this. Let's see how this works. Now, as we can see here, we've already set up our project and we've already created our class with a main method. Now, the first thing that we're going to do in order to use graphical user interfaces, we have to import a lot of various packages in order to make this easier. So one of the first ones we're going to do is going to import java.awt.star. Next, we're going to import javax.swing.star. And finally, import java.util.star. Each one of these packages include various types that we're going to use in order to make our life a lot easier. Now, one thing to keep in mind when we start developing these graphical user interfaces, we're effectively going to be creating windows. Now, understanding this a little further, a window is divided up into first a frame. This frame is going to contain panels that we're going to be drawing. In order to set up this window, we now have to create a frame. Inside of my main method, I'm going to generate a new JFrame, just call it frame, and I'm going to construct this as a new JFrame and just put a title in here like Sierpinski's carpet. JFrame is a class that can construct new objects that are called frames. Now, this is a good time to look in the Java Development Kit, the JDK, because you can see that these classes have a lot of pre-built methods that we can utilize. One of the first ones is I'm going to set the size of this frame, the size of this window basically. Frame.setSize, and I'm just going to pass in 900 by 900. Now, once again, the frame acts as a container that holds various types of panels, drawing regions. In a lot of cases, these are called components. As we are creating a very specific kind of a drawing area to draw this Sierpinski carpet, what we're going to do is use inheritance in order to make a specific version of this drawing region. So we're going to take Sierpinski carpet and have this extends canvas. Canvas is going to be the type that we use to draw. Now this Sierpinski carpet is a canvas. Now we can utilize all the methods that are built into this canvas. So what we're going to do first is create a new instance of the Sierpinski carpet. We'll just call it SP, and we'll construct this as a new Sierpinski carpet. This constructs an instance of this class, which is a canvas. Now, as this is a canvas, we can take frame and add this to our frame. Then we can frame.setVisible to true. Now, one other quick detail. Creating this window has a set of resources associated with it. So in order to make sure that we dispose of those resources, we need to set frame.set default close operation to jframe.exit_on_close. Now that we have this, well, we can see what this does, which really isn't all that much. It creates a new window that doesn't have anything inside of it because we haven't defined how to draw this Sierpinski carpet. The next thing that we're going to do is start filling in how we're going to draw this. There's a couple of things that we have to keep in mind. There are some methods that are already defined inside a canvas. We also recognize that some of these methods are not called by us. Some of these methods are called by the JFrame in order to set all of this up. This is why, once again, reading through the JDK, the Java Development Kit, becomes very valuable in order to solve a lot of these problems. Understanding how this system works. Like, for instance, inside of every canvas, we have this method called paint. What we're going to do is override that method in order to paint the Sierpinski carpet. The way that this is called is public void paint. And reading through the documentation, I can see this paint requires a parameter called a graphics G. this graphics G is initialized by the set of components and the frames through various calls. We use this graphic G in order to draw elements to our canvas. What we need to do now is create the recursive method that uses this graphics G in order to draw the carpet. We're going to go ahead and separate this out into a different method. We're going to call this one public void draw carpet. Now in our problem definition, we have to be given a starting coordinate x and y, and then the size of the side. So our parameters is going to follow int x and int y, int side. And now there's one more parameter because we do need to draw this to our canvas. So in this case, we need to pass a graphics G into this method. Now we are not calling the method paint. Paint is going to be called by some of the other objects that we've created here. But we need to make sure that our version of paint draws the carpet. So in this case, we need to call draw carpet. Starting at the origin, our top left position is assumed to be 0, 0. The side of this is going to be this dot get size dot height. We know our width and height are the same, so we can pick either or. And from there, we also pass along the graphics G that we can draw. Now inside of our recursive method, the first thing we're going to do is calculate the side. So we needed to take this side and divide it into 3 horizontal, 3 vertical spaces. So we're going to take this int, and we'll call this the subdivision, and set this equal to this side divided by 3. Now that we have that, we have all of the information in order to draw that center square. We can do this by calling our graphics G, and now this has a lot of methods that we can explore in order to draw items to our canvas. One of the most relevant ones is we have this one called fill rectangle, where we simply pass in an x, y coordinate and a width and a height, and it draws this rectangle. So starting from this x, we need to draw this center square, which means we have to start from the top left coordinate of this square. So starting here, given this x and y, we know we got to start this from x plus this subdivision. In other words, this side divided by 3 in order to scoot it 1/3 left. Now y needs to be scooted 1/3 down, so we also add this subdivision here. We know the width and the height are the same, which is 1/3 of the side, the subdivision. And now we have the first part of the problem where we have divided the region into 9 separate squares and we have filled in the center region. Running this, we can see that we have divided this into the 9 parts and filled in the center square. Now the next thing that we have to do is we need to recursively call this once again, but given different x and y coordinates and a different side. One element that we have to keep in mind as we are doing recursion is we need that halting condition. For argument's sake, we're just going to use a pixel limit. So if this subdivision still happens to be greater than or equal to, let's say, 3 pixels, then we'll keep going. Now what we're going to do is concern ourselves with the top squares. Let's take a look at the top left one first. If we call draw carpet. Now as this is the top left, the coordinate starting at that top left position is the same x and y. The big difference now is this side is 1/3 of the original side, so we're just going to use the subdivision, and then also pass in g here. This once again takes care of all of the top left recursive calls. Let's just see how this works. Now by doing that, as you can see, this filled in this first center square. Then, dividing this region right here into 9, it filled in this center square. Dividing this even smaller region by 9, filled in this one, filled in this one, filled in that one, filled in that really tiny one up there. Now let's do top middle. So once again, draw a carpet. Now in order to get the top middle, the x position has to change, because its starting coordinate is not the same x position. It's moved over by 1/3 of the side. So if I take this x plus this subdivision, now I have scooted over from this x 1/3 and starting there. Now as this is still the top row, the y position remains the same. Same subdivision, same graphics G, and this is top middle. Now running this. As you can see, this took care of all the cases involving the middle square. Let's continue to write this, filling in the rest of the recursive calls. All they're doing is changing the x and y coordinate from where we're starting, and also the size of the side. So, draw carpet. X plus this subdivision, but this time times 2. Because if we're doing top right, this has to start 2/3 over from where we originally started. Same y, same sub, same g. This is top right. Now let's do the middle row. Draw carpet. If we're doing middle left, the x remains the same. However, now the y position has to be moved down by 1/3. Y plus the subdivision, sub, and g. This is middle left. There is no middle because the middle has already been filled in. There's only a middle right. Draw carpet. Now in this case, we have to x plus the subdivision, but this time times 2 because it's 2/3 away. Y plus the same subdivision so we can scoot it down by 1/3, given this subdivision, and g. This is middle right. Now let's worry about the bottom row. Once again, draw a carpet. Starting from the same x position, now we have to move the y coordinate down by 2/3. So y plus the sub times 2. Subdivision and g, and this is bottom left. Draw carpet. Now if we're doing bottom middle, we have to do x plus the subdivision, 1/3, y plus 2/3, subdivision times 2, with the subdivision and g. Bottom middle. And finally, the last recursive call. Draw carpet. X plus the subdivision times 2, so 2/3 over, and y 2/3 down, with the subdivision and g. This will be bottom right. Now let's see if this works. Running this, it looks correct. We have made this seemingly complex image by fairly simple code. Recursion allows us to elegantly solve these problems by finding a solution to the same problem, but a little smaller, and then applying that solution to the greater problem. We're going to continue to use this technique in more advanced data structures. Until then, I'll see you next time.